Okay, this is lesson 4.3a. So when you select members from a sample at random, we can certainly make an inference about the population. Now, what makes that inference more exact or a better kind of prediction? It would be surprising if you got it exactly, right? We just took a small sample. You might think we might be close to the population, but the truth, the actual mean of the sample or whatever we're studying, probably is not, exactly there. Okay, so sampling variability is talking about what is sampling variability. It's a term we're going to use. So it refers to the fact that different random samples of the same size from the same population produce different estimates. That's absolutely true. So if you were trying to figure out the true percentage of blue M&Ms, and you open up a pack of M&Ms, you counted how many blues, and you got the percentage. Then you open up a different pack of M&Ms of the same size, so same number of M&Ms. Most likely you would get two different percentages in those two samples. And that's what it's saying. It's saying if you take a small sample, that it might not be accurate to I don't know how many, they probably have a number they produce, 20% or something are blue. Some particular percentage is a certain color. And so when we open up a small sample, we might get that exact percentage. It's possible, but more likely we're going to get something somewhat close. Depending on how big the sample is that we take, it might be closer if we take more, is the idea of today's lesson. So sampling variability definitely depends on the sample size. So how big is your sample? How many M&Ms are you testing? How many, or whatever it is you're testing. So larger random samples, no big surprise, tend to produce better estimates that are closer to the true population value or mean that you're studying than smaller random samples. So if you only sample, 5 M&Ms and you're trying to figure out the percentage of blue, you're not going to get a very accurate sample. But if you sample 500, wow, now you're going to get a pretty accurate sample, a much better prediction for what the true percentage of blue M&Ms might be. So this is actually, so they had a percent of red beads that were sample size, N means a sample size of 20. So they reached into the bag, got 20 beads, figured out the percentage of red beads, and plotted each one of those points is one sample of 20. And they took the mean of those samples, like what percentage were red when they picked out 20 beads from the bag. However, then they redid it with a sample size of 100. That means they took 100 beads randomly out of the bag and measured the proportion of red beads. You can see that it's a more precise estimate. So similar shape, but you can definitely see that, this one ranges from 20 to 40. The other one ranged from 10 to 50. So more precise. They come up with similar, you think about it, you do enough of a sample size of 20, you're going to figure out about what the mean is. The mean is probably around 30, it looks like, for the percent of red beads for this particular bag of beads. But you just have more precise estimates when you have a larger sample size. That's the concept of today's lesson. So how much do NFL football players weigh? I would imagine there's a wide range because quarterbacks, linemen, receivers, those are all different weight guys there. Some are bigger, some are smaller. So they took a random sample of 50 NFL players, and the average weight was 244.4 pounds. Wow. Okay, so do you think that's the true average weight of all NFL players? What do you think? You took a sample of 50 players, so that's not terrible. But did you nail it the first time? You took one sample of 50 players. Do you think you got it exactly? Probably not, right? Different samples of size 50 would probably produce different average weights. So one might be 260, one might be 220. I don't know. It's going to range. You have some kind of range of values that if you kept taking samples of size 50 randomly, you would probably get different results every time. So it would be surprising if you got it exactly, just taking one sample of 50. Which would more likely give an estimate close to the true average weight, a random sample of 50 or a random sample of 100. Hope this is getting easy at this point. Certainly, the random sample of 100 is going to be a more precise estimate. It's not going to be perfect either, but again, the larger the sample, the more precise the estimate. They tend to be closer to truth when the sample size is larger. So well-designed experiments allow for inferences about the cause and effect. So this is now talking about cause and effect. So there are two ways to explain why the average response for one group is different than another group. The treatment does not have a different effect for the groups, and the difference in the responses happen because of chance variation. So sometimes we explain the results. We say, well, maybe it was just chance variation. And sometimes we say, you know what, we think the treatment caused a difference in the average response of the group. So that's also the rub. I mean, how do you figure out, how much was due to chance and how much was actually the treatment actually made a difference, right? So sometimes you can kind of look at how unusual your results are. But when the observed results are too unusual to be explained by chance alone, the results are called statistically significant. It's kind of like saying, when you have something statistically significant, it's hard to say, then you've got something where you go, wow, maybe this treatment really is effective, right? So you want that when you do a study, you want it to be statistically significant. So you want results that are more extreme than just chance alone. So we can kind of test chance alone. We can actually do that sometimes. So I think this was an example in the book. If you do the reading, is talking on a cell phone while driving more distracting than talking to a passenger? That's actually, I feel like, an interesting question. So they designed an experiment. They used 48 undergraduate students as subjects. The researchers randomly, that was easy for them to do, right? They had probably students who were their subjects. They randomly assigned half the subjects to drive in a simulator while talking on a cell phone. The other half have to drive in a simulator while talking to a passenger. That's weird. You have to talk. You have to keep talking during this simulation. Okay, so one response was whether or not the driver stopped at a rest area that was specified by researchers before the simulation started. The table shows the results. So it looks like 12 of the 24 cell phone folks, so about half, stopped at the rest area. 21 out of 24 passenger folks stopped at the rest area. So that was something they talked about beforehand. I guess they remembered to do it. Sometimes when you're talking to people, you kind of forget some things. You don't think about everything that you need to be thinking about. And so that's one way of saying, hey, are you alert? Are you doing this? And so just preliminary results, wow, it looks like the cell phone may be more distracting, but let's just kind of see what they say here. So calculate the difference, passenger and cell phone, in the proportion of students who stopped at the rest area. So you say 12 out of 24 cell phone users stopped, 21 out of 24 passengers stopped. Those are, get the percentages and find the difference, right? So you're going to find those two percentages, 0.75 and 0.5, or half of those. And so we found a difference of 0.375. So 100 trials of a simulation performed to see what differences and proportions would occur only due to chance variation. So there were 33 stoppers and 15 non-stoppers that were randomly assigned to two groups of 24. There are 3 dots at 0.29. Explain what these dots are in context. So we don't see that graph, do we? I think we almost kind of need to see that graph, but at 0.29, when you just did a simulation, which is chance alone. Simulation is when you didn't actually perform an experiment, but it's just like studying chance. If it was just by chance alone, there would be three people who were at 0.29. So when we assume the type of distraction doesn't matter, in person or on the phone, there were 3 simulated random assignments where the difference in the proportion of students who stopped at the rest area was 0.29. So that's not that many here. So use the results of the simulation to determine if the difference in proportions for part A is statistically significant. Again, I really think it would have been helpful to see see if I can get that. Okay, so I took a screenshot of the book. If you see in the bottom left there, now that's the simulation results. Again, that's from chance alone. That's not from experiment. This is just simulation. And you can see those 3 dots on the right at 0.29. That was the most extreme example they had, is 0.29 actually. So using the results of the simulation to determine if the difference in proportion for part A, which I think was 0.375. So 0.375 is not even on our simulation. So there were no results that extreme in our simulation. So because of that, we would probably say never occurred in the simulation, right? 0.375. The difference is statistically significant. It is extremely unlikely to get a difference this big simply due to chance variation in the random assignment. So we can say that there's causation here, right? We can say that maybe it is more distracting to be talking on the cell phone than to be talking to a person next to you. So that's not probably that surprising, but at least a little bit surprising result there, I would think. So how many likes for Selena Gomez? So evidently Instagram is a thing called likes, and you can, she has 103 million followers. Wow. Okay, so how many likes did she get for each Instagram post? So in a random sample of 30 posts, the average number of likes was 3.1 million. Evidently, she is an influencer. So do you think that 3.1 million is the true average number of likes for all Instagram posts made by Selena Gomez in 2016? So, it might be close-ish, but I don't think that's the actual average, right? We took a relatively small sample size, 30 posts, and so we hope that might be close-ish, but certainly we don't think it's the actual average. Which would be more likely to give an estimate closer to the true average number of likes for all Instagram posts for Selena Gomez in 2016, a random sample of 30 posts or a random sample of 100 posts? What do you think? I'm thinking 100 because you're going to have a more precise estimate. They tend to be closer to the truth. They're still not maybe the truth, but when you have a larger sample size, you get something that's closer to the truth. This is actually kind of interesting. Mythbusters did a thing about yawning. So they said they had a person who gave a yawn seed. So the experimenter actually yawned, I think on purpose, so that tried to cause other people to yawn, because that's the idea, right? If you see someone yawning, you seem maybe to be more likely to yawn, I guess. I think that would be the thing they're testing. So the 16 subjects out of the 50 were not given a yawn seed, so they didn't have anything like that. What happened? So evidently, when given a yawn seed, 10 out of 34 people yawned. When having no yawn seed, so no one was kind of baiting them to yawn, only 4 out of 16 did that. So you want to calculate the difference in terms of percentages. So you do 10 out of 34 and subtract 4 out of 16, whatever those percentages are in your calculator, and you get a difference there. So if you did that, that would be 29% minus 25%. There's a 4% difference in those two numbers. So now we have a simulation. So off to the right here, you see that dot plot. So that is a dot plot of that's if chance alone. It's called a simulation, simulated differences. It doesn't mean on the graph on the left, that chart, they did an actual experiment there, right? They had a yawn seed, that was the treatment. They had an experiment, they took the data. Here, this is just random chance. So if it was random chance, this is what might happen. These are reasonable results that you might get if you did this by random chance. And so 0.04, where does that fit in here? So that fits right about in the middle. The median looks to be right about 0.04, it looks like. So about half of the folks in the simulation, which again is just simulated, were 0.04 or bigger of it, more extreme. So, and by the way, it says there are 5 dots at 0.23. Okay, I see those 5 dots. What do those mean? So in the simulation, in the assuming that yawning is not contagious, we just There are 5 simulated random assignments where the difference in the proportion was 0.23. So is it statistically significant? No, I mean, that's right in the middle almost of where the simulation was. 0.04 is not that unusual at all. So we don't think, according to this, it doesn't seem like a yawn seed really made a difference. The interesting thing is Mythbusters actually said there was a difference. They said, yes, the yawn seed made a difference. But when you actually look at it statistically, 56 of the dots were 0.04 or greater, which is over half of them. It's quite plausible to get a difference as big as 0.04 simply due to chance variation in the random assignment. So that's our lesson for today.